Hello everyone, welcome to my series of videos on integral calculus or calculus 2. So we begin the series with our video on antiderivatives. So in calculus 1 we saw how to derive functions. So we know how to derive functions in one way. Now calculus 2 we're essentially going in the opposite direction. Instead of deriving function, we're anti-deriving functions. And we're going to see why this is useful to us. So let's begin with the definition. So a function capital F of x is called an antiderivative of f of x for all x in an interval I if capital F prime of x is equal to little f of x. Okay, so what is this telling us? So let's consider a function capital F of x to the 4. And let's take the derivative of this function, giving us capital F prime of x is equal to, so we know the derivative of x to the 4 because we saw power rule in Cal 1. So we drop the 4 and subtract the exponent by 1, giving us 4x cubed. Okay, but now what we do is we look at this and we want to work backwards to get to this point. So instead of starting with the x to the 4, now we're going to be starting with 4x cubed, and we're asking ourselves, what can we take the derivative of in order to give me this? This is antiderivatives, essentially going in the reverse order. Okay. But there's an issue. Notice that this is the outcome for the derivative of x to the 4. But what if we had some functions called capital F again? What if it was x to the 4 plus 1? What would the derivative be? This gives us, we know if we take the derivative of x to the 4 plus 1, the derivative of a constant is 0, and the derivative of x to the 4 is 4x cubed. Notice that if we're working backwards, if we start off with capital F of f prime of x equals 4x cubed, this gave us x to the 4, yet here when we antiderive, it gave us x to the 4 plus 1. And if I added a plus 2 here, we would have the same derivative. So notice that we're starting with the same function, 4x cubed. If we antiderive, if we go backwards, there's many possible answers. Okay, so this is the first observation you have to make, which leads us into our next theorem. So let's go ahead and take a look at that. So the theorem states that if capital F of x is an antiderivative of little f on an interval I, then capital F of x plus c is what we call the general antiderivative, where c is a constant, any real number, okay, of f on I. So essentially when you're antideriving, what you're going to get is not a function, but we call a class of functions or a family of functions, okay? So you don't have one single option, you have many. Essentially the function plus some constant that's potentially there, because remember, when we're taking the derivative, you might have a constant that's there that might get cancelled out. When you're anti-deriving, you don't know if that constant's there or not, okay? So you have to consider it. So let's consider this example over here again. So we said if we have capital F of x is equal to x to the 4, and we just take the regular derivative, then capital F prime of x is equal to 4x cubed. We know that, power rule. And again, if we have capital F of x is equal to x to the 4 plus 1, we take its derivative. Again, it gave us the same antiderivative. All these are the same. We get 4x cubed. Again, if we consider the function capital F of x is equal to x to the 4 minus 10, the derivative of minus 10 cancels, so we get the same antiderivative. Okay, so now the notation that we're using is we're starting with this side. We're starting with 4x cubed. So if we call little f of x 4x cubed, then what's the antiderivative? The antiderivative, which we're denoting by capital F of x now, is going to be equal to x to the 4 plus c. So what could I take the derivative of to give me 4x cubed? That's the question that we're asking. But at this point here, we should be noticing a trend. How could you get from here to here? Try to think of a pattern. What's happening to the numbers and try to get from here to here. We know the power rule. Try to find the opposite direction. So the power rule for antiderivatives now. Okay, and don't forget your plus c. So now when we're anti-deriving, we get a class of functions or a family of functions plus c. If I were to graph this, essentially what we would get is, so if we consider the graph, we have something like this, y, x, and if we consider the function that we're dealing with, the x to the 4, the function looks something like this, sort of like a quadratic. This is f of x equals x to the 4. And what we mean by a class of function is that we're essentially taking the exact same function and raising it and dropping it. Okay, so instead of having passing through the origin, we're going to subtract it by 1, so the function might pass through -1 or +3. Okay, and why does this make sense that we're considering functions which are basically moving upwards and downwards, not to the left and to the right? Well, think about the derivative. The derivative corresponds to the slope of the tangent line. So if we consider any point, any x value, let's call it here, and we look at the slope of the tangent line, just because the function's been raised, we would expect that no matter where we go at this value here, the slope of the tangent line would always be parallel, no matter which function we're dealing with. Okay, I didn't draw it properly here, but this is the idea. So this would look something like this. Okay. And this is the idea for this term. Okay, let's continue and look at a couple of examples. So here, let's go ahead and find the general antiderivatives of the following functions, the basic functions that we already know. So if we have the function f of x equals e to the x, what's the antiderivative of e to the x? So you're asking yourself, what function do you have to take the derivative of? And that's going to give us e to the x. Well, that's pretty simple. We know that the derivative of e to the x is e to the x. That's the forward direction. If we go backwards now, the derivative of e to the x is e to the x. That means the antiderivative of e to the x is still e to the x. So if you said that, good job. But it's wrong. It's not e to the x on its own. Remember, the theorem that we just saw, you have to add a constant. Don't forget the plus c. Okay, so the antiderivative in its general form is capital F of x equals e to the x plus c. Okay, let's do the same thing for sine and cos. Try to find the general antiderivative of sine and cos. Okay, so in a previous video, I gave you a pattern. We know that the derivative of sine is cos. This is the derivative. And then the derivative of cos is negative sine. And then the derivative of negative sine is negative cos. Okay, this was a pattern that we saw. And then if you take the derivative of negative cos, you're back at the top. That's sine. Okay, this is taking the derivative. Now what we're doing is we're taking the antiderivative. So we're using the same pattern, but just backwards. So now if we're asking what's the derivative of sine, the antiderivative of sine, well, instead of going downwards, now we're going upwards. So really we're going this way. Antiderivative. So the antiderivative of sine is actually negative cos. And the antiderivative of negative cos is negative sine, and so on and so forth. So the same pattern is useful to write down for derivatives and antiderivatives, Cal1 and Cal2. Okay, so if we're looking for the antiderivative of cos, well, the answer is sine. Okay, so the antiderivative of cos is sine, and the antiderivative of sine is negative cos. Okay, from our pattern. So let's go ahead and write that. Let me erase the pattern. So capital F of x is negative cos of x. It's in the general form, so don't forget to add your plus c. And same for here. Capital F of x is equal to sine of x. Again, plus c. This is an abusive notation. I'm using capital F of x for all these different types of functions. But this is just to denote that this is the antiderivative. I'm using capital F of x for the antiderivative. Okay. In a sense, you're asking yourself, what could I take the derivative of to give me cos of x? Well, if I take the derivative of sine, this is how you could always check your work, is if you take the derivative of sine, you get cos of x. And if you take the derivative of a constant, we know that's 0. So we get the original function. Okay, so now that you know, now that we're learning the antiderivatives, you could always check your work by just, once you get your answer, take the derivative quickly and see if it matches what you started with, okay? So we saw the power rule. F of x equals x to the n. So what we did for the power rule is we dropped the exponent, subtracted it by 1. Now we're trying to antiderive. What's the opposite direction? How do we do this in the inverse direction? So the antiderivative, what was the example that we saw? We saw the example from 4x cubed. It went to, when we derived, we got x to the 4 plus c. What did we do to get from this stage to this stage? Well, when we took the derivative, you dropped the exponent and subtracted it by 1. Now we're doing the exact same thing, but in the opposite direction. We're adding 1 to the exponent. That's how we got from 3 to 4. So we're adding 1 in the exponent. So whatever the number is in the exponent, we add 1 to it. And then how do we get rid of the 4 in the front? Well, we essentially divide by whatever number is in the exponent. Okay, so in the exponent here we have a 4. We're going to divide by 4, and that's going to cancel out this 4 that's sitting over here. Okay, so the antiderivative for power rule, it's x to the n plus 1 divided by n plus 1. Okay. And notice this doesn't work for n equals to -1, because if we had -1 here, we'd be dividing by 0. So this doesn't work. For the case where n equals -1, we'll consider that case on its own. But this is the general antiderivative for the power rule. Okay. So this one's very common. Remember this. You add 1 to the exponent and divide by whatever number's in the exponent. Okay. Let's look at the case where we have -1 in the exponent. So before we continue with this example over here where the exponent is -1, let's just verify our work. We saw in the previous example that the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. How can we be sure this is right? Well, let's take the derivative of this and see if we get back what we started. So if this is the antiderivative, then the derivative of this has to be this. Don't forget your plus c. So let's go ahead and take its derivative. So if we're taking the derivative of this, the constant is out, so we don't have to worry about the constant. This part here, what do? We drop the exponent. So the n plus 1 comes on the bottom, n plus 1. We subtract the exponent by 1, so the n plus 1 becomes just n, because n plus 1 minus 1 cancels the 1's, leaving us with just n. And then we have the n plus 1 on the bottom. And as I stated before, the constant's out, the derivative of a constant is 0, and these guys cancel each other, leaving us with just x to the n. And that's what we started with, okay? So again, be sure to always check your work. I think it's a good idea to invest time to check your work, especially in the beginning when you're new to antiderivatives. Check your work by deriving, okay? So this makes sense. This is what we started with. Good. Let's keep going. So in this next example over here, we have x to the exponent -1. We said that it doesn't work in this case here because if we had exponent -1, this would cause us to divide by 0. So how do we solve this? So what you're essentially asking yourself is, what could you take the derivative of that's going to give us this function, x to -1, or you could also think of it as 1 over x. Okay. And the answer to that question is ln. We know the derivative of ln of x is 1 over x. Let's put absolute values, just to be a bit more precise. So the antiderivative of 1 over x is ln of x. Okay, so this one here you have to be careful. So when you have exponent to -1, don't use power rule. You'll get a division by 0. That's how you know it's not power rule. And in this specific case, it gives us ln. The antiderivative of 1 over x is just ln of x plus your constant in its general form. Okay. The next one that we have, e. Consider the function secant squared. Think of its derivative, and f. Let's think of the function secant tan. So what do we have to take the derivative of to get secant squared? Well, we know that the derivative of tan is secant squared. So that means the antiderivative of secant squared is tan. And because it's the general form, again, we add our constant plus c. Okay. All of these formulas have to be memorized, okay? So we know it in one way, we just have to keep them in mind for the other way. The function that we start with is secant tan. The antiderivative of secant tan, again, you're asking yourself, what do I have to take the derivative of? What function do I take the derivative of? And it's going to give me secant tan. Well, that is secant. Because we know the derivative of secant is secant tan. So that means the antiderivative of secant times tan is secant. And then we don't forget our plus c. Okay. So these are some examples, some basic examples of derivatives that we have to keep in mind. But you should be getting the hang of it. And again, always check your work to ensure that once you get your answer here, take the derivative to see if you get what you started with. If you don't, you made a mistake. If you do, you have the right antiderivative. Okay, let's keep going. So in this next example over here, it says to find the general antiderivative of the function f of x equals to cos of x plus square root of x, all that divided by x squared. So I encourage you to pause the video, try to solve this on your own. First thing to notice is that we have a division. In antiderivatives, we don't have any rules. We can't apply product rule, quotient rule, chain rule, none of that. We don't have that for antiderivatives. Okay, so our trick right now, our strategy is to deal with each term individually. So let's rewrite this. So we're setting ourselves up. The cos of x is not an issue. We know how to antiderive that. Here we have a fraction, so we split it. So we'll deal with x over x squared plus square root of x. We could rewrite it as x to the 1/2 over x squared. Okay, so rewrite roots as exponents like we did in Cal 1. And x over x squared, we could rewrite this as, just by simplifying, 1 over x. You cancel out an x on the top and the bottom, giving us 1 over x. And here we could simplify. If we subtract the exponents, we have a 1/2 minus 2. So without a calculator, a 1/2 minus 2. Think of 2 as 2 over 1. Find a common denominator. 1 over 2 minus 4 over 2. Giving us negative 3 over 2. So this could be rewritten as x to the negative 3 over 2. Okay. So we split it up, we subtract the exponents, and we wrote it in this form, because now this is, we could use our power rule for antiderivatives. Even the 1 over x, you could rewrite it as x to the negative 1, but this is a bit of a trick. Remember, power rule doesn't work for x to the negative 1 when the exponent's negative 1. So I like to leave it in this form to remind myself that power rule doesn't work. Okay, so we'll leave it as 1 over x. And now we ask ourselves, what could I take the derivative of? What function do I have to take the derivative of to get a cos? So this means that the general antiderivative is the antiderivative of cos is not negative sign, it's just positive sign. Okay, so we're not deriving, we're anti-deriving. We're in the opposite way. So we get sine. The antiderivative of 1 over x is ln of x. And the antiderivative over here, what we do is we add 1 to the exponent and divide by that number. So right now the exponent is negative 3/2. If you don't have a calculator, you have to do this by hand. You add 1. So we find a common denominator. 1, think of it as 1 over 1. The common denominator is 2. So 3 over 2 plus 2 over 2. That gives us negative 3 plus 2 is negative 1 over 2. So it's negative 1/2. So this gives us plus x to the negative 1/2, because we add 1 to the exponent and then we divide by whatever that number is in the exponent. So we divide by negative 1/2. And because we're finding the general antiderivative, don't forget all these cases have a plus c. We combine it to one giant plus c at the end. Okay, so the sin x had a plus c, the ln had a plus c, and this term had a plus c. We just combine them all together and call it a big constant over here. Okay, next, we cannot leave our answer in this form. We have to simplify. So the general form is sine of x plus ln of x. Here we could drop the exponent, and dividing by 1/2 is the same as multiplying by 2. So it's negative, we get minus 2 over x to the 1/2, or square root, plus c. And this is the general antiderivative. Okay, let's keep practicing. So in this next example over here, it says to find the particular antiderivative of the function f of x equals square root of x times, in brackets, 3 plus 5x, close bracket, given that capital F of 1 is equal to 5. So here, the thing you have to notice is that it's asking for a particular solution, not a general solution. So we're not looking for a class of functions, we're actually looking for just one. And this is why they give us an initial condition. F of 1 equals 5, that's an initial condition. This means that we have to not express our answer as a class of function, leaving the plus c. We actually have to go find the value of c. So let's go ahead and do that. So let's begin by finding the antiderivative. Again, square root of x is multiplying all this. We don't have a product rule for antiderivatives yet. We'll learn about it later. Right now, all we know is to deal with each term individually. So let's go ahead and do that. So we're going to set ourselves up, and we're going to distribute the x to the 1/2. Square root of x, again, I always rewrite it as x to the 1/2. And now we distribute it, giving us 3 x to the 1/2 plus 5x. We're multiplying the same base, so we add the exponents, 1/2 plus 1, do it on the side. Think of 1 as 1 over 1. This gives us 3/2. So here we just set ourselves up, and now we use power rule for antiderivatives. So we add 1 to the exponent and we divide by whatever that answer is. So capital F of x, the general solution is 3 times x to the 1/2 plus 1, which we just saw is 3/2, divided by whatever's in the exponent, 3/2, plus 5. Again, the constant multiples, we leave them, we ignore them. We'll leave the 5 there. Here we add 1 to the exponent, so 1 plus 3/2 is 5/2, and divide by whatever is in the exponent, so 5/2. And since it's the antiderivative, capital F of x, we add our plus c. Okay, now let's go ahead and simplify this. On the top, you could think of this as a fraction divided by a fraction, so we can multiply by the reciprocal. This is very common. So 3 times, instead of 3 over 2, we're going to multiply by 2 over 3, x to the 3/2, plus same thing will be here. We'll leave the 5. Think of it as 5 over 1 divided by 5 over 2. The 5 over 2 flips, so it's times 2 over 5, x to the 5/2, plus c. Notice that the 3's cancel and the 5's cancel, leaving us with 2 x to the 3/2 plus 2 x to the 5/2 plus c. Okay. This is equal to f of x. So if it asks us to find the general solution or the general antiderivative, we're done. Since it's asking us for a particular antiderivative, we have to actually go ahead and find the value of c by plugging this in. Capital F of 1 equals 5 is really telling us when x is 1, the y is 5. So we're substituting our x values with 1, and we're substituting the f of x, or y, with 5. So let's go ahead and do this. So 5 equals 2 times 1 to the 3/2 plus 2 times 1 to the 5/2 plus c. 1 to the 3/2 and 1 to the 5/2 is just 1. So this leaves us with 5 equals 1 times 2, which is 2, 1 times 2, which is 2, 2 plus 2 is 4. So we get 5 equals 4 plus c. Subtracting the 4 on the other side leaves us with c equal to 1. This implies that c equals 1. And now we have our particular solution. So this answer over here is the general solution. Replacing the c with 1 back into the general solution gives us our particular solution, the particular antiderivative. Okay, so make sure you understand the difference between general solution and particular solution. Whenever you're given an initial condition, it's a particular solution problem. Okay, and that's the answer. Let's keep practicing. So in the next example, we have to find f of x given the second derivative f double prime of x is equal to 6x minus 4, and they give us two initial conditions. They tell us that f prime of 1 equals 0, and they tell us that f of 2 equals 2. So we have to go find the original function, having given us the second derivative. We know that if we have f of x, and we take its derivative once, we get f prime of x, and if we take its derivative again, we get f double prime of x. So this is taking the derivative twice, d dx. So now, starting with here, to get back to the original function f of x, we have to antiderive twice. Antiderive once to get f prime of x, then antiderive twice to go get the original function f of x. That's our game plan. Let's go ahead and do that. So to go get f prime of x, let's take the antiderivative of this function here. So let's go find f prime of x. So we have 6x. So we can think of this as 6x to the 1. So we just use power rule, but for antiderivative, so we add 1 to the exponent, giving us x2, and then we divide by whatever the exponent is, so divide by 2. And then we have minus 4. How do we take the antiderivative of minus 4? Or think of it as, what's the derivative, what function do I have to take the derivative of to get simply just negative 4? Well, the answer is minus 4x. Okay, why? How do we get minus 4x? Where does that x come from? In a sense, we're using still the general, the power rule for antiderivatives, because you could think of negative 4 as negative 4 times x to the 0, right? X to the 0 is 1, so it's like multiplying by 1, and now we use power rule here. So we add 1 to the exponent, 0 plus 1 is 1, and divide by 1, giving us negative 4 times x to the 1 divided by 1, but we don't have to put the division by 1, so that gives us just negative 4 x to the 1, and the exponent of the x we don't have to write, we know it's there. So it gives us just negative 4x. Okay, so essentially, if you're taking the antiderivative of a constant, you just add an x, incorporate an x. Okay, and since this is an antiderivative, we have a constant that might appear. Now our job is to go find that constant. How do we find that constant? Using our first initial condition. We know that f prime of 1 is equal to 0. That means in the first derivative, which is what we have here, if we substitute x with 1 and y with 0, that's going to allow us to find our constant c. So let's go ahead and do that. Substituting this with 0, we get 0 equals 6. Well, 6 divided by 2, we could just write 3 right away. And x is being replaced with 1. So 1 squared minus 4 times 1 plus c. 3 times 1 squared is 3 minus 4 times 1 is 4. So 3 minus 4 is negative 1 plus c. We get 0 equals negative 1 plus c. Bring the negative 1 over, you get 1 equals c. So we found the actual value of c. This is 1. So this is work you do on the side. And we know this value is actually 1, thanks to our first initial condition. And 6 divided by 2, I'm just going to simply write 3. Okay. So we found our first derivative, f prime of x. It's this function here. Let's go find our second derivative and apply our second initial condition. Sorry, not the second derivative, the initial function f of x. So we're going to antiderive to get f of x. So if we take the antiderivative of 3x squared, you add 1 in the exponents, you have 3x to the 2 plus 1 is 3, and then divide by whatever's in the exponent, dividing by 3. Same thing here, 4, we think of it as x to the 1, so write the 1 if it helps you. You add 1 in the exponent, so you get x squared, divided by whatever's in the exponent, so divide by 2. And 1 is the same thing that we saw with the negative 4, we basically just add an x. And there's another constant that appears, let's call it d. Okay. Now our job is to go find d. How do we do that? Substitute using our second condition. Notice that this is not f prime of 2. F prime goes to the first condition, f of 2 goes into this function here. Okay, so make sure you apply the right initial conditions to the appropriate functions. So here you're replacing x with 2 and y with 2. Replacing y with 2, you get 2. Here, 3 divided by 3 is 1, so we're just left with 2 cubed. Minus 4 divided by 2 is 2. And then we're substituting the x with 2. So we get 2 squared plus 1 times 2 plus d. So what we get is 2 equals 8 minus 8 plus 2 plus d. The 8's cancel, the 2 goes over, that means d. So we subtract this 2 over, 2 minus 2 is 0, d equals 0. Okay, so d is gone. So the original function f of x, erasing all this, we know d is equal to 0, so we don't even write it. So the original function f of x is just 3 divided by 3 is 1, so we get x cubed minus, let's rewrite it here, minus 2x squared plus x. Okay, and that's the answer to the question. Okay, let's look at our last example. So in this final example over here, we have to find the original function f of x, given the second derivative f double prime of x equals 20x cubed plus 12x squared plus 4, and here they give us two initial conditions, f of 1 equals 5 and f of negative 1 equals negative 1. The challenge with this one is that the two initial conditions that are given pertain to the original function f of x, not the first derivative. Okay, so pause the video, try to solve it on your own, see if you're able to solve it. So since we're given initial conditions on the original function, let's go ahead and antiderive this function twice to get the original function. So the first derivative, if we antiderive once from the second derivative we end up with to the first, it gives us 20x to the 4 divided by 4 plus 12x to the 3 over 3 plus 4 times x plus a constant. Okay, let's simplify that, giving us 20 divided by 4 is 5, x to the 4 plus 4x cubed plus 4x plus c. We can't do anything because we don't have any information on this, so let's go ahead and antiderive once more to find f of x. So the original function f of x is 5x to the 5 divided by 5 plus 4x to the 4 divided by 4. So we're adding 1 to the exponent, dividing by it, adding 1 to the exponent, dividing by the number, adding 1 to the exponent here, so plus 4x squared divided by the 2, and then plus cx, where this is a constant, so the antiderivative of a constant, we just add the x, and then lastly we have plus d. Okay, so the issue with this function is that we have two unknowns, but that's okay, we could solve it because we have two initial conditions. So we could create two equations, we have two unknowns. This is high school math, we could solve this. So the function that we're dealing with, f of x, is x to the 5 plus x to the 4 plus 2x squared plus cx plus d. Using the first initial condition, this is saying that x is 1, y is 5. So replacing this with 5, we get 5 equals 1 to the 5 plus 1 to the 4 plus 2 times 1 squared plus c times 1 plus d. Okay. So here 1 to the 5 is 1, 1 to the 4 is 1, 2 times 1 squared is 2, so 1 plus 1 plus 2 is 4, and we can bring that over. 5 minus 4 is 1. So we get the equation 1 equals c plus d. Okay, so let's write that on the side, and let me erase for some room. This is the original. From the first initial condition, we get this equation. From the second initial condition, now we're using the fact that x is negative 1 and y is negative 1. So substituting here negative 1, we get negative 1 to the 5 plus negative 1 to the 4 plus 2 times negative 1 squared plus c times negative 1 plus d. Negative 1 to the 5 multiplying the negative 1 by itself 5 times ends up with a negative. Negative 1 to the 4 multiplying itself 4 times, that's an even exponent, so this becomes positive. 2 times negative 1 squared, negative 1 squared is positive 1 times 2 is plus 2. C times negative 1, it's minus c, and plus d. So what we get here is negative 1, 1 they cancel. 2 goes over, so we get negative 3 equals negative c plus d. Okay, so that's our second equation. Negative 3 equals negative c plus d. There's different ways to solve this. You can use elimination method, substitution, or even comparison method. I think the easiest one here to do is probably elimination method. Seeing that you have 1 equals c plus d, let me erase more of this. Actually, I'll keep that over there. We have 1 equals c plus d, and then we have negative 3 equals negative c plus d. What you can notice is that if you add both equations to each other, if we add these two equations, we have c and negative c. They're going to end up canceling each other out. Or if you want, you could cancel out the d's by subtracting both equations from one another, and that would cause the d's to cancel out. I think it's easier to add, so let's go ahead and add. So 1 plus negative 3 is negative 2 equals c plus negative c, same number, opposite sign. They cancel, and d plus d is 2d. So now we have one equation with one unknown. So we could solve for d. Dividing both sides by 2, we get d equals negative 1. Okay, so we found the value of d. Now let's go find the value of c. How? Go back to any of the first two equations and solve for the missing variable. So let's use the equation 1 equals c plus d. We now know that d is equal to negative 1. Let's substitute that. So 1 equals c minus 1. Bringing the negative 1 over, it becomes 2. So c equals 2. And now we found the original function. So we could substitute our c with 2. So this gives us 2x. And we know our d is equal to negative 1 minus 1. So the original function f of x is equal to x to the 5 plus x to the 4 plus 2x squared plus 2x minus 1. Okay, and that's the final answer. So I hope this video will help. Keep practicing, and I'll see you in the next one.